In this lesson, we're looking at the inverse trigonometric functions, and we've used these already, but there's a bunch of details about them that we haven't worried about. We've just kind of used them in our calculator without really fully understanding some fine details, some technicalities about them. So we're going to take a look at these for a little bit. At first, it might seem kind of tricky or confusing or weird to just kind of hang in there for a little bit. Eventually, we'll kind of boil it down to some nice, fairly simple rules. We need to kind of dive into it for a little bit first to try to understand what's going on here. Okay, so first of all, just to review, the idea was a regular trig function. You input the angle and it outputs some sort of ratio, and so we used an inverse function to reverse that, to switch the input and the output. It would allow us to input the ratio so that we could find out what the angle was. Okay, so a regular trig function, we know the angle, it tells us the ratio. The inverse trig function, we know the ratio, and the function tells us the angle. Okay, there's actually multiple names for these. So the -1 symbol here could be used for the inverse function. It could also be called arcsine. Okay, these are the exact same thing. 6 of one, half a dozen of the other. There's zero difference at all between them. They are completely identical. Just two different ways of expressing the exact same function. Okay. Part of the reason why we have this alternative naming is that the -1 symbol is actually a little bit awkward. Um, I actually kind of hate that they use this symbol. Kind of have to apologize for mathematicians everywhere that we've done this to you, because what you're going to see, and you might have seen this a little bit already in Algebra 2, and if not, we'll be seeing this next chapter. What we do a lot of times is we put exponents on trig functions. We write them in this spot right here. When we want to say sine of x squared, we write it as sine squared of x. Because like if you had sine x squared, that would mean sine of x squared. And so if we want to not just square the input, square the x, if we want to square the whole thing, we're we're too lazy slash efficient to write those parentheses every time. And so we're going to put the squared there to say that it's just the whole thing that's being squared. A cube, same thing. Most of the time, if you put a number here next to a trig function, it means that whole function is getting squared or cubed or whatever the exponent is. The one exception is if you put the number -1 there. If I put the number -1 there, it means arcsine. It means the inverse sign. It does not mean sine to the -1. It does not mean 1 over sine of x. So there's a little bit of awkwardness there when we use the -1. That's part of why some people like to use this other name for it instead. Okay, but they're often just used interchangeably. Okay, so let's take a look at this. Let's start to kind of dive in to why there's going to be a little bit of trickiness with these. Okay, so here's the idea: if we start out with this, if we know a ratio and we're trying to find an angle, there's actually an infinite number of solutions. All right, let's review why. So sine being a half, you should know that from the unit circle. On the unit circle, the angle that has a y coordinate of 1/2 would be pi over, it's either 3, 4, or 6, right? Pi over 6, right? Well, of course, sine could be positive in multiple quadrants, and so we could, told you 1,000 times in this class, look at 8STC. So the first quadrant angle is that pi over 6. There's also a second quadrant angle that has a pi over 6 reference angle, whose sign would also be positive 1/2. And so if we're in the second quadrant with a pi over 6 reference angle, that's going to be 5 pi over 6. And if you need to take a minute to figure out that that's 5 pi over 6, that's okay. I'm going to be kind of skipping through that from now on. But if you need to draw it and do like pi minus pi over 6 and figure out the 5 pi over 6, or if you need to count around like 1 pi over 6, 2 pi over 6, 3 pi over 6, 4 pi over 6, 5 until you get to 5 is the next one that doesn't reduce. Whichever one of those strategies you need to figure that out. If that takes you a minute, that's okay. You can always pause the video, right? But the more and more you get comfortable with these, the more and more you'll just be able to say, oh yeah, second quadrant, the pi/6 angle, that's 5 pi/6. Okay. All right, so we've got two solutions. What about infinite solutions? Why are there infinite solutions? Right? Well, remember that there's not just one angle. If I draw pi/6, if I picture pi/6 here, there's not just one angle that lands in that spot. Okay? What if I went in a full circle? Or what if I went backwards? There's an infinite number of angles, an infinite number of ways to rotate and land in that same spot. We call those coterminal angles. Right? So I could find a coterminal angle. I could add 2 pi. And of course, adding 2 pi would be the same thing as adding 12 pi/6. And I could get 13 pi/6. That would be a coterminal angle with pi/6. That would be an angle that landed in the same spot, that would have the same xy coordinates on the unit circle. And so it would have the same trig values. It would have the same sign. Okay? I could find a coterminal angle for 5 pi/6. I could add 12 pi/6, get 17 pi/6. Okay? I could do negative angles. I could subtract. Instead of adding 2 pi, I could subtract. Let's subtract 12 pi/6. If I subtract, I'll get negative 11 pi/6. Subtract 12 there, I'll get negative 7 pi/6. And we could keep doing it, right? You could keep adding full circles. You could have 25 pi/6, 37 pi/6. You could keep going on forever. There would be an infinite number of angles that have this sine value. Right? Here's the problem though. Inverse sine is a function. When I go into my calculator, let me put myself in radian mode here. When I go into my calculator and I type inverse sine of 1/2, how many answers should it give me? It should only give me one answer. It's not going to give me an infinite number of answers. When I hit enter, it's not like there's just going to be a list that keeps going and my calculator is just going to be kind of stuck because it's going to be trying to keep giving me answer after answer after answer. It has to give me just one answer. It's a function. Inverse sine is a function. So for this input, there has to be only one output. Okay? There it is in decimal form. Okay, well, which one of these angles do you think it is? Which one, let's say you're the mathematician that invented inverse trig functions. Out of all these angles, you get to pick which one is going to be the one that the calculator would spit out, that is the answer for inverse sine. Well, if you had to pick one of these angles, you would probably pick the simplest one. You would probably just pick pi/6. So even though there's an infinite number of angles that have this sine value, inverse sine has to be a function. It has to have only one output. It has to pick one of those angles. So we pick the simplest one. We pick the pi/6. All right. If you don't believe me, you can check here. If I type pi/6 in my calculator, there you go. It's that same decimal right there. Okay. All right, so it's kind of the same idea as this right here with solving these kind of quadratic equations here, these simple ones. So we would square root both sides, and of course, when you square root both sides, you have to say plus or minus. Okay, 3 squared is 9. Negative 3 squared is also 9. Okay, so if I solve this equation, I get these two different solutions, plus or minus. But square root is a function. And so if I just ask you, what is the square root of 9, you can only tell me one answer. When I type square root of 9 in my calculator, it has to just give me a single number. It's a function. One input, one output. It can't have multiple things. It can't change its mind between multiple answers. Square root of 9 is just 3. Even though the equation has multiple solutions, the function has only one output. Right? That's the issue that we're running into with these inverse trig functions. Okay? Now, when it is positive values like this, it's going to be pretty simple that we just pick the reference angle, basically the quadrant one really simple angle. When it's a positive value like this that we're trying to find the angle for, there's not going to be much of a question of which angle we pick. Okay, where it's going to be a little bit trickier is what if we want to get a negative value, find an angle for these negative values. It's not always going to be quite as clear which angle we pick for these. Okay, all right, so if I want cosine to be negative a half, well, first let's just think about cosine being a half. Think on your unit circle, the angle that has an x coordinate of 1/2. Is it pi over 3, pi over 4, pi over 6? It'll be pi over 3. Okay. All right, well then we want it to be negative though. So let's think about ASTC. Well, cosine to be negative, that could be the second or the third quadrant. All right, and again, if you need a minute or two, go ahead and pause the video and you can think about what angles are in the second or third quadrant that have a reference angle of pi over 3. What we're looking for here are 2 pi over 3 and 4 pi over 3. Pi over 3 reference angle in the second and third quadrant. Okay, of course, there'd be infinite solutions though, right? We could go in full circles. We could add 2 pi, add 6 pi over 3. We'd have 8 pi over 3, 10 pi over 3. Could go in a full circle backwards. Subtract 2 pi, subtract 6 pi over 3. Have negative 4 pi over 3, and a whole bunch more angles, infinite number of angles, okay? The question is, which one do we pick? Okay. Well, for this one, we'll just pick the first one again. We'll pick 2 pi over 3. Okay, this one's not, doesn't seem too tricky at this point. Just pick that smallest angle. Okay. Here's where it's going to get a little bit trickier now. Okay, so sine of theta is negative a half. So for sine to be a half, think on the unit circle, the angle with a y coordinate of a half. We already saw that. We already saw that would be pi over 6. So we know the reference angle is pi over 6. But we want sine to be negative. So we have to think about ASTC, third or fourth quadrant. Okay. And so again, if you need a minute, think about that. That's okay. You can always pause the video. But that'll be 7 pi over 6 and 11 pi over 6. Thing is, actually, neither of those angles is arcsine of negative half. Right? Before, all this talk of coterminal angles, adding, subtracting 2 pi was just to show you there's actually an infinite number of answers. It's not just two answers that we had to choose between, an infinite number of possibilities. But really talking about those other ones is kind of silly. Of course, we're going to pick one of those first angles there. This one, though, we actually don't pick either of those angles. So what we're kind of going to be looking for is the smallest in absolute value angle. So here we could just say the smallest angle. Here, both of these angles, those involve a fairly large amount of rotation. You've rotated pretty far by the time you've gotten to 7 pi over 6 or 11 pi over 6. I mean, even to 7 pi over 6, the first one there is more than 180 degrees. You rotated more than 180 degrees by the time that you get to that angle. We want a different angle that involves a lot less rotation. Okay? You think of another angle that's coterminal with one of those that involves a lot less rotation. What it's going to be is it's going to be a negative angle. If we take a look at this 11 pi over 6, if we subtract 2 pi, which is the same thing as subtracting 12 pi over 6, we're just going to get negative pi over 6. And of course, there's an infinite number of other angles, but that's the angle we're looking for. Negative pi over 6. That's the angle out of this whole infinite long list of angles. That's the angle that has the least rotation. That's the smallest in absolute value out of all those angles there. Okay. So I've shown you a few examples of how we've kind of picked the angle. But we don't want it to just be kind of guesswork of just, well, list out a bunch of angles and just kind of pick which one we seem is the best. We need a hard and fast rule here. Okay. And we'll boil it down to something pretty simple. But first, I want to just give you a little bit of an idea of where the rules come from taking a look at the graphs. right? And we'll compare what happened with x squared and square root of x first, and then we'll look at the trig ones. So here's the issue, actually. Try to think back to when we did inverse functions. Right? Not every function had an inverse function. Remember, inverse functions swap the x and the y, and a function can't have two y's for the same x. And so what happened was, if you have a function like y equals x squared, when you switch it to its inverse, you switch x and y, right now you have two x's with the same y, and that's okay. Two x's with the same y, that's okay for a function, but you switch it to the inverse, and now you have one x with two y's. That's not okay. So the inverse of y equals x squared is actually not a function. Okay. We used a vertical line test to see if something was a function or not. To see if the inverse was a function, we used a horizontal line test. All of these functions fail the horizontal line test. Not one of these functions as a whole could have a function that's an inverse. Well, wait a minute. We've been doing it. Here's cosine inverse right here. We did it. It's in my calculator. My calculator has inverse sine, inverse cosine, inverse tangent, and they work as functions. But what we're saying is that these don't have a inverse that's a function. All right, what's going on? So let's back up. Let's take a look at this one. Okay, so x squared. So what we wanted was, we wanted to be able to have an inverse for the squaring function. We wanted to be able to say, okay, something squared is 1,000. What's the something? We wanted a function that could do that for us. Okay, that's where square root came from. Okay, the problem is we couldn't work on the whole function. What we have to do is restrict the function. We have to cut the function down so that we're only looking at part of it. Right? So what we did is we said, well, let's just look at the positive values. Let's have our inverse, our square root function, only tell us the positive answers. If I just look at that part of the graph, that part of the graph is 1 to 1. It would have an inverse that was a function. It passes the vertical and horizontal line test. If I switch it to the inverse, it is a function now. Okay, so we just look at part of the original function and look at that for our inverse function, our inverse values. Okay, so square root of x isn't the inverse for all of x squared. Square root of x is just the inverse for that part of the x squared function. Okay, it only goes backwards for some of the values. It can only switch input and output for some of the values. Right? It's going to be the same thing for these trig functions. We can talk about inverse cosine, but it's not the inverse for the entire cosine function. It's the inverse for only part of the cosine function. Let's try to figure out how we cut it. For x squared, it was a pretty obvious choice, right? I mean, they could have decided that they wanted square root of x to give negative values. They could have decided they wanted square root of 9 to be -3. It just wouldn't make as much sense. You know, we've got geometry. We want to be able to have sides of squares that are positive values. So it made a lot more sense to pick positive values. That was an easy choice. Pick the positives, ignore the negatives. What about cosine of x? How can we chop that function down in a way that kind of makes sense and that it'll pass the horizontal line test and have an inverse? Okay. Well, I mean, we probably want to start around 0. We probably want to have this, like this right here is quadrant 1. That right here is like our pi over 6, our pi over 4, our pi over 3. So our angles are our x here, so like pi over 6, x pi over 6 here, x pi over 4 here, x pi over 3 here. We probably want to have those kinds of angles. Okay? And then what we also want is we want to have both positive cosine values and negative cosine values. So what we do is we take this part of the function right here. Okay. So for positive cosine values, we take quadrant 1 angles. And then for negative cosine values, we take quadrant 2 angles. Okay? You can see that's the choice that we made right here. We wanted inverse cosine for a negative value. We used this quadrant 2 angle right there. Okay? All right, what about the other ones? See, for sine, could we make the same choice? For sine, could I cut it down to just quadrant 1 and quadrant 2 like that? I couldn't. There'd be a couple problems. First of all, the inverse would still not be a function. This would still fail the horizontal line test. Also, that would only give me positive sine values. I want to have both positive and negative sine values. Okay? I also want it to be like one continuous section of the graph. So I didn't want it like back here, we didn't want to choose 7 pi over 6 because that would be like down here. We don't want to have like this section of the graph and then like skip that section of the graph and then take this section. We don't want to like have some things be pi over 6 quadrant 1 here and then some things be 7 pi over 6 quadrant 3 down there and have this like missing section of quadrant 2 in the middle. Okay? So instead what we do is we choose this nice continuous section of the graph right here. That passes the horizontal line test, and it includes both positive and negative sine values. Okay? Again, when it's positive, we just use quadrant 1. We just use our nice simple pi over 3, pi over 4, pi over 6 reference angles that we know very well. Then for this one, for negative values, instead of choosing quadrant 2, we choose quadrant 4, and we choose the negative version of the quadrant 4 angles, like this negative pi over 6 right here. All right? We don't want 7 pi over 6, 11 pi over 6. We chose negative pi over 6. Notice we couldn't have done that for cosine. For cosine, if you tried to do the negative quadrant 4 angles, cosine's positive in the fourth quadrant, right? So we had to make a different choice for cosine than we did for sine. But for tangent, we can do the same choice. For tangent, we haven't even talked about inverse tangent at all yet, but inverse tangent will work the same way as inverse sine did. We make the same choice. We always choose quadrant 1. We like those quadrant 1 acute, nice normal angles that can be reference angles. We like those. And then for negatives, we choose quadrant 4, and we choose the negative versions. Okay. All right. So graphically, this is what it looks like. Okay? If that was super confusing to you, sorry. Don't worry about it. Let's boil it down to some nice simple rules here. Okay. So kind of one guideline is you want to choose the angle that has the least amount of rotation. So if you're thinking about a few possibilities, if you're thinking about like 2 pi over 3 or 4 pi over 3, choose the smaller absolute value one. Choose the one that has the least rotation. Okay, that's why we choose negative pi over 6 instead of these. This one has less rotation. It's smaller in absolute value. It's the angle that's closest to 0. Okay, and so what that's going to look like in practice is if it's positive, it's going to be super easy. Okay, so positive, we just say pi over 6 or pi over 4 or pi over 3. We just choose the quadrant 1 angle. That's not going to be a problem. The positive ones are going to be easy. It's the negative ones you have to think about. Okay, and so if we have negative inverse sine and inverse tangent, we just do a negative quadrant 4 angle. Okay, so both inverse sine and inverse tangent, we're just going to kind of stick a negative on the angle. Let's see what I mean in a second. Inverse cosine is going to be the one that you're going to have to keep straight. That one's going to be the one that's different. Inverse cosine is going to have to be quadrant 2 when it's negative. Okay, negative inverse cosine, you need a quadrant 2. You could also choose to use these formula, and we'll do some examples here. I promise this is not going to be as tricky as it might sound. It's actually kind of a couple pretty simple rules once you see this in practice. Okay? You could also look at these formal definitions here. Right? So inverse sine has to always be between negative pi over 2 and pi over 2. Inverse cosine between 0 and pi. Inverse tangent also between negative pi over 2 and pi over 2. We've got the parentheses here because tangent is undefined at those endpoints, at those pi over 2 places. Okay? All right. So again, inverse sine of a half, we just say pi over 6. Positive, we just give that first angle there. Okay. For inverse sine of a negative, notice all we did was we stick a negative on the angle. Inverse sine of a half is pi over 6. Inverse sine of negative half negative pi over 6. Inverse sine and inverse tangent of a negative, you're just going to stick a negative on the angle. Okay? Inverse cosine of a negative, we couldn't just stick a negative on pi over 3. So that would be fourth quadrant, cosine's positive fourth quadrant. Inverse cosine of a negative, what we needed was this quadrant 2 angle. We chose the quadrant 2 angle for inverse cosine of a negative. All right, so let's look at some examples of this. Okay, so in this top row here, where we want a positive value, they're all going to be super easy. Okay, you just, as long as you know your unit circle, that's why I said it was super important. Okay, so you just need to have memorized what angle has an x coordinate on the unit circle of root 2 over 2. Pi over, it's got to be either pi over 6, pi over 4, pi over 3. Okay, this one's pi over 6. Or sorry, what am I saying? Pi over 4. Sorry about that. Where did that come from? Okay, so inverse cosine of root 2 over 2, that's pi over 4. Pi over 4 is the x coordinate, root 2 over 2. And then that's it. You don't overthink it. Okay, when we want an angle and we want this value positive, just the very first one, the reference angle, the simple one. Okay, inverse sine of root 3 over 2, think on your unit circle. What angle has a y coordinate of root 3 over 2? Pi over 3. Okay, simple, done. Okay, arctangent, and again, you know, if I said sine of theta equals root 3 over 2, there's infinite answers. But for this inverse sine, you just kind of give this first one. You don't think about others. You don't think about multiple quadrants. Inverse sine's a function. Just give me this one output. Okay. For arctan, you have to think about a little bit more. Remember, tangent is y over x. So you want y over x to equal 1. Well, that means that y has to equal x. Okay? So think on your unit circle. Think about pi over 6, pi over 3, pi over 4. Which one had the y and the x being the same thing? And that was pi over 4. Right? But so when we want this positive value, when we have this positive value inside the inverse function, we just give this first angle we think about. There's not, you got to know your unit circle, but otherwise there's not much to it. Okay. Well, what about for the negatives? For inverse sine and inverse tangent, it's going to be pretty easy as well. Right? So we still think about, okay, inverse sine root 3 over 2. When is the y coordinate root 3 over 2? It's got to be some sort of pi over 3 angle. And then the question is, which one? Just like over here, we know arctan of 1 is pi over 4. We know when we want the tangent to be 1, it has to be some sort of pi over 4. Then the question is, which one? Well, for both of these, it's super easy. Inverse sine, inverse tangent, just stick a negative on it. That's it. You don't gotta think about it. You don't have to, write out a bunch of possibilities and think through it. That was just to kind of show you the idea. Inverse sine, inverse tangent, just stick a negative on it. Okay. Inverse cosine is the one that's different. Okay. If you stick a negative on it, you would get a quadrant 4 angle. Cosine's positive in the fourth quadrant. That's no good. So the thing that you really have to kind of remember is for inverse cosine of a negative, you've got to remember to give the one that's in quadrant 2. Okay, negative inverse cosine quadrant 2. That tends to be the one that people can forget because it's the one that's a little bit different. Okay, inverse cosine of a negative value, give me a quadrant 2 angle. Okay, so we know the reference angle has to be pi over 4 because that's when cosine is root 2 over 2. We want the x coordinate to be root 2 over 2, that's pi over 4. So then you just have to figure out what's the quadrant 2 pi over 4 angle. Again, if that takes you a minute, that's fine, but it'll be 3 pi over 4. Okay, so positive, easy. Inverse sine, inverse tangent of a negative, stick a negative on the angle. Inverse cosine of a negative, look in quadrant 2. That's what it boils down to. Why don't you try several of these here? Why don't you try to determine the value of those 6 trig functions? Remember, they're functions, so it has to be a single value. I'm looking for a single angle for each of these. What's the one angle that's the answer? Go ahead and give those a try. All right, and so here are the answers. All right. So again, these ones that were positive, you don't have to think about that too much. Those are straightforward. Just give that first angle right there. Um, Inverse tangent of a negative, we just stick a negative on it. So we knew it had to be pi over 3 to have the y be root 3 over 2, the x be 1/2, and then we just stick a negative on it. Here we knew the reference angle had to be pi over 6. So that's when x is root 3 over 2. Then we want quadrant 2. That's 5 pi over 6. Okay. If we want sine to be 1, we wanted the y coordinate to be 1. That's straight up. That's pi over 2. This is the one that gets a little bit tricky for some people sometimes. So straight down, you're used to thinking of as 3 pi over 2. Problem is arc sine of a negative is supposed to be a negative angle. Right? It's supposed to be in negative pi over 2 to pi over 2. So 3 pi over 2 doesn't work. Sometimes people try to stick a negative on 3 pi over 2. Well, negative 3 pi over 2 would actually be straight up, not straight down. So what we needed here is negative pi over 2. Negative pi over 2 is coterminal with 3 pi over 2, and it is in the interval that we needed it to be in. Right. Just a few last problems here. Kind of get a 2-for-1 special here. We'll give you 2 problems in one. So you just have to work your way inside out. So you start with this right here. So cosine of pi over 2. Well, pi over 2 is straight up. So it's the point 0, 1. The x coordinate is 0. So that right there is 0. And then we just have to find arc sine of 0. Okay. So arc sine of 0, we want an angle that has a sine of 0. Well, if sine is going to be 0, the y coordinate is going to be 0. And so if the y coordinate is 0, we're on the x-axis there. So out of all these angles that could be at either of those two spots that could have a sine of 0, a y coordinate of 0, the one with the least rotation, the one that's closest to 0 is 0. So the answer is 0. Okay. On this one here, we start with the inside. So we want cosine to equal 0. Again, what this is asking for here, we're looking for cosine theta equals 0. This one down here was looking for sine of theta equals 0. Okay, so if we want cosine to be 0, we want the x coordinate to be 0. So we're looking for straight up or straight down. Okay, so the one that we're going to choose out of all those angles is going to be pi over 2. And then we just have to find the cosine of pi over 2. That's going to be 0, the x coordinate of pi over 2. So notice these just cancel out here. Cosine, cosine, inverse, kind of like squaring and square rooting, can just cancel each other out. Just be careful, they don't always cancel each other out. So this one, tangent and inverse tangent, they're actually not going to cancel each other out because of the domain issues. Okay, kind of like square root of negative 5 squared is not negative 5, it's positive 5. Same thing here, because of the domain issues, these aren't just going to cancel each other out. So just work your way through them. Okay, so tangent of 3 pi over 4. 3 pi over 4 is in the second quadrant, and so tangent is going to be negative. And we know for a pi over 4 angle, the x and the y are going to be either the same or, one's positive, one's negative, that kind of thing. So if the x and the y are the same, y over x will be 1. Okay. And then because we're in the second quadrant, ASTC, tangent has to be negative. And then arctangent of negative 1, we already did that earlier on. Arctangent of a negative, we stick a negative on the angle. This right here is negative pi over 4. Okay, so even though some of these will cancel each other out, function and inverse cancel each other out, they don't always. So best just to always start on the inside and work your way out.